Welcome to the deep dive. Okay, so today's mission, if you choose to accept it, is tackling maybe the most fundamental disconnect in mapping. Coordinate systems versus map projections.
Right.
You've got your GPS giving you latitude and longitude, right? That's location. But then your map app tells you distance in meters or feet.
Totally different concepts.
They seem like they should be the same thing for the same spot, but they're really speaking different languages. Why?
Well, it really boils down to the Earth itself. I mean, the basic problem is that the Earth isn't, a perfect sphere. It's mathematically modeled as an oblate ellipsoid.
Sort of squashed.
Exactly, slightly squashed. But even that's a simplification. If you actually measure its true physical shape based on gravity, you get this lumpy, uneven surface we call the geoid.
Whoa, hang on. Okay, so ellipsoid is the smooth mathematical shape we use.
The reference.
And the geoid is the actual bumpy, gravity-defined reality.
You got it.
Yeah.
The ellipsoid is the smooth ideal we calculate with. The geoid is the messy truth.
Okay. So for location on that 3D shape, we use the Geographic Coordinate System, GCS.
That's the one. Latitude and longitude. Angular measurements.
Degrees, minutes, seconds, or now mostly decimal degrees, right? For computers.
Yeah, DD is much easier computationally.
But here's the catch, isn't it?
Yeah.
GCS is great for pinpointing a spot.
Perfect for that.
But you can't reliably use those angles to measure distance or area.
Exactly. And the Y is key. Think about the lines of longitude, the meridians.
They all meet at the poles.
Right. They converge. So 1 degree of longitude is a huge distance at the equator.
Yeah.
But it shrinks to basically nothing near the North or South Pole.
Okay, that makes total sense. So if I, use my phone's lat long and try to walk a perfect square, say 100 meters north, then 100 meters east, using just those coordinates, the math, like basic Pythagorean theorem, would be wrong because that east distance isn't constant.
Precisely. The angular distance changes depending on your latitude. That inconsistency makes GCS useless for simple geometry.
So how do we fix that for calculations?
We need a datum. It's basically an agreed-upon reference frame. It defines the specific size and orientation of the ellipsoid model we're using.
So the datum is the specific mathematical lie about the Earth's shape we all agree on for consistency.
That's a good way to put it. You have local datums, which might be super accurate for, say, North America.
But not elsewhere.
Right. And then you have global standards like WGS 1984. That's the one GPS uses. It tries for the best average fit across the entire globe.
And this brings up that huge issue, datum shift.
Oh, absolutely critical. If you mix data using different datums like an old paper map and your modern GPS.
The same physical lamppost could have coordinates hundreds of meters apart.
Easily. You have to be consistent with your datum, otherwise your data is garbage.
Okay, so datum nails down the 3D reference. Yeah. But we still need flat maps for measuring distance easily. That's where projected coordinate systems, PCS, come in.
Exactly. We need to perform a map projection. We take the 3D GCS coordinates, the latitude and longitude,
and mathematically flatten them onto a 2D plane.
Right. Into simple Cartesian coordinates, x, y, using linear units we can actually measure, like meters or feet. Then we can finally use things like the Pythagorean theorem reliably.
So what's a common PCS we might encounter?
Well, for accuracy in measurement, the gold standard is often UTM, Universal Transverse Mercator.
UTM.
Instead of flattening the whole globe at once, which causes massive distortion, UTM slices the Earth into 60 narrow vertical zones, each only 6 degrees of longitude wide.
So it minimizes distortion by only projecting a small strip at a time.
Precisely. Within each zone, locations are measured in easting and northing, basically X and Y coordinates in meters. It's essential for things like surveying, engineering, military ops, anywhere you need really accurate ground measurements.
But even with clever tricks like UTM zones, we can't escape the fundamental problem, can we? Didn't Gauss prove you literally cannot flatten a sphere onto a plane without some kind of distortion?
That's the unavoidable truth. You always have to choose what you're going to mess up.
So what are the choices? What properties can a map preserve?
There are basically 4 main properties map makers juggle. Shape, which we call conformality, area, or equivalence. Then there's distance and direction.
And you can't have them all perfectly on a flat map.
Nope. Maximize one and you inherently distort the others. It's always a trade-off.
The classic example is always Mercator, right? The one everyone recognizes.
Yeah, Mercator is famous. It preserves local shape really well, and lines of constant compass bearing are straight lines, great for sailing navigation.
But the cost is huge distortion of area, especially near the poles. Greenland, Looks bigger than Africa.
Exactly. It massively exaggerates area as you move away from the equator. Contrast that with something like an Albers equal area conic projection.
Okay, what does that one do?
As the name suggests, it preserves area. All the land masses have the correct relative size. That's vital if you're making, say, a map showing population density or resource distribution. You need the areas to be accurate. But
It must distort shape or direction then.
it does, especially over large areas. Shapes look a bit more warped compared to Mercator.
Okay, so wrapping this up. For you listening, the takeaway is location on the globe needs a datum, like WGS 84 for your phone.
That fixes your position on the 3D model.
But actually measuring distance or area on a flat map requires a projection, like UTM or Albers or Mercator.
And the type of map projection you choose depends entirely on what kind of error, what kind of distortion you're willing to live with for your specific task.
Right. No single flat map tells the whole truth.
Which leads to a final thought. Knowing that every flat map lies, when you pull up Google Maps or Apple Maps for driving directions, think about that projection they're using, usually some variant of Web Mercator built on WGS 84. What specific property do you think they absolutely must prioritize for your navigation task? Shape, area, local distance. And why is sacrificing, say, the true relative size of continents completely acceptable when you're just trying to find the quickest way to the supermarket? Something to chew on next time you ask for directions.